Next, we're going to look at another method for obtaining unknown information about a triangle, but this time what we're going to be using is trigonometry. And we can use trigonometry on any right-angled triangle, so long as we know the length of one side and at least one of the angles in addition to the 90-degree angle. So the triangle in the top left corner represents a right-angled triangle because one of the angles is 90 degrees. But the triangle in the bottom left-hand corner isn't a right-angled triangle. One of the things that I stated in the previous video was that we could turn this into two right-angled triangles by separating the triangle into two like so. So although not all triangles are right-angled triangles, we can still apply Pythagoras and trigonometry in certain instances. So in order to define trigonometry, I'm going to give you an angle in the bottom left-hand corner, which I'm going to call theta. Now the very first thing that we do whenever we're approaching a trigonometry problem is we need to label the triangle. Now the way that we label the triangle is we need to label the hypotenuse, we need to label the opposite, and we need to label the adjacent. Now the way that we do this is the hypotenuse is always the longest side of the triangle, and we can see that by inspection. The longest side is here. Another way of thinking of the hypotenuse, or the longest side, is that it's always directly opposite the right angle. Next up we have the opposite. Now the opposite is always opposite the angle that's given or the angle we're trying to find. So it's opposite angle theta. That's our opposite there. And then the remaining side is the adjacent. So we label the hypotenuse, then we can label the opposite, and then we can label the adjacent. Now once our triangle's labelled, we can then introduce the equations for trigonometry, and there's only 3 to remember. And the way to remember them is by remembering Sohcahtoa. I'll just write this out. Sohcahtoa. So represents sine, where sine theta equals opposite over hypotenuse. Ka represents cosine, where cos theta equals adjacent over hypotenuse, and toa represents tan, where tan theta equals opposite over adjacent. They're the only 3 equations that you need to remember for trigonometry. Providing you remember them and you can rearrange equations, you can find any unknown lengths and unknown angles in that triangle. So let's go straight into an example. So in this case, we know that the longest side of the triangle is 6.5 meters. And we know that the angle at the top is 25 degrees. Now we're going to use trigonometry to find the length E and to find the length F. It doesn't matter that they're called E and F, these are just arbitrary values that I've chosen for this example, but we're going to find E and we're going to find F, the length of those 2 sides. So first of all, if we begin, we need to label the triangle. Okay, so labelling the triangle, the first thing that I said was that the longest side is always the hypotenuse. Also the side that's opposite the right angle. Now the side that's opposite the angle that's given is called the opposite, and in this case the angle that's given is the angle at the top, therefore the opposite is F. That side is the opposite. And the adjacent on the triangle this time is A, the remaining side. So we know our hypotenuse, our opposite and our adjacent. Next we have our 3 equations which come about as a result of Sohcahtoa. So in order to find the length of F, or the opposite, I have 2 choices. I could either use so, because I'm trying to find the opposite, or I could use toa, because I'm trying to find the opposite. But in this instance, I know the length of the hypotenuse, therefore I'm going to use so, which is sine theta equals opposite over hypotenuse. Now I'm trying to find the length of the opposite side. Therefore, to get O on its own, I need to times by h each side of that equation. Because at the moment, I've got O over h, and I want O on its own. Well, when I times the left-hand side by h, I get h times sine theta, or it's also written as just h sine theta. And when I times the right-hand side by h, I'm just going to be left with O. Therefore, O equals h sine theta, which in this instance is 6.5 sine 25 degrees. Now please note that it's important that you make sure that your calculator is in degrees mode. All calculators have two different options. You can either express angles as degrees or radians, and the way that you know which mode your calculator is in is at the top of the display there will either be a capital R or there will be a capital D. We're looking for a capital D for degrees in this instance. So 6.5 sine 25 on the calculator is 2.75 to 2 decimal places. Therefore, the length of the opposite, or the length of F, is 2.75 metres. Next, we're going to find the length of E, and the way that we're going to find the length of E this time is using our second equation, because we're trying to find the adjacent, and we know the hypotenuse. Therefore, we're going to use K, which is cos theta equals adjacent over hypotenuse. I'm just going to continue this down in the bottom left-hand corner. If cos theta equals the adjacent over hypotenuse, and we need to get the adjacent on its own, we need to times each side of that equation by the hypotenuse. So times h each side. That's going to give us h cos theta equals A. Therefore, in this instance, A equals h cos theta, which equals 6.5 cos 25, which equals 5.89 to 2 decimal places. Therefore, E equals 5.89 metres, and we've found the two unknown lengths on that triangle. So let's take a look at another example of finding unknown lengths on a triangle using trigonometry. And just before we begin this one, I want to make it clear that you don't need to memorise all of the different ways of finding the opposite and all of the different ways of finding the adjacent and the hypotenuse. The key thing is to begin to understand how to apply the process. So we look at what we don't know, we look at what we do know and select our equations from there. More often than not, there's more than one method in order to determine our unknowns. So in this case, I'm going to find J and I'm going to find K, and my starting point is to label that triangle. As we've said on a few occasions, the longest side is our hypotenuse. The side opposite the given angle is the opposite, and the remaining side is the adjacent. And now we can write out Sohcahtoa, which we're going to use to determine which equations are best to use. Okay, so in this instance, the first side that I'm going to try to find is K, which is the opposite. So I've got two options. I can either use SO, because opposite appears in that equation and I'm trying to find the opposite, or I can use TOA, because O appears in that equation and I'm trying to find the opposite. They're the only two equations I can use directly in order to calculate K. The issue this time is that I only know the length of the adjacent and not the length of the hypotenuse. So knowing the length of the adjacent means I'm going to use this equation here, TOA. Well, TOA states that tan theta equals opposite over adjacent. And this time I'm trying to find the opposite. Well, to get O on its own, I'm going to times each side by A this time. And when I times by A, I'm going to get the opposite equals A tan theta. Okay, so I've selected my equation and I've rearranged that equation to make the O, or the opposite, the subject. And now I'm just going to plug in my values. The adjacent is 122 millimetres. Tan of our angle, which is 19.2. And that gives me the length of the opposite, which is 122 tan 19.2. or 42.48 millimetres. The reason I know it's millimetres in this instance is because the length of A was given in millimetres. Therefore, K equals 42.48 millimetres. Next, I'm going to find the length of J, which happens to be our hypotenuse. So this time, I know the opposite and I know the adjacent, and I'm trying to find the hypotenuse. Well, if I'm trying to find the hypotenuse, I can either use this one here, because the hypotenuse appears in that equation, or I can use this one here. I know the opposite and I know the adjacent, so it makes no difference which one of those I use. But this time, I'm going to use sine theta equals opposite over hypotenuse. Now, to get the hypotenuse on its own, I'm going to need to do two steps, because the thing I'm trying to find is on the bottom of that equation. Now, if you recall from the algebra topic, whenever the thing we're trying to find is on the bottom of the equation, we can do something called the reciprocal of each side. Well, when I recip the left-hand side, I'm going to get 1 over sine theta. And when I recip the right-hand side, I'm going to get the hypotenuse over the opposite. The top becomes the bottom and the bottom becomes the top. Therefore, my next step will be to times each side of the equation by O. And I'll be left with the hypotenuse equals opposite over sine theta. Once we've reached that stage, it's simply a case of plugging in our values, because we know the opposite. The opposite is our 42.48 that we found previously. And we know the angle is 19.2 degrees. And that will give us the length of our hypotenuse, which is 129.19 millimetres. Therefore, J is 129.19 millimetres. And we've found all of the unknown lengths on that triangle. I'm just going to go back one stage, and I'm going to go back to the point where I'd found the length of the opposite, K, but I hadn't yet found the length of J. Now, the reason why I wanted to do this was to show you how interchangeable Pythagoras and trigonometry can often be. As you can see here, we know the length of the two shortest sides. We know the length of this shortest side here is 122 millimetres, and we know the length of this shortest side here is 42.48 millimetres, and we want to find the length of J, which is the longest side. Now, if we label this triangle a little differently, in the same manner we did when we did Pythagoras' theorem, our longest side is always called C, and our two shortest sides are called A and B. We then took our Pythagoras equation, which was C squared equals A squared plus B squared. And in this case, we're trying to find C. C squared is A is 122, B is 42.48. Therefore, C squared, running that through our calculators, is 1688.55. And then square rooting each side will give us C. So square rooting the answer gives us 129.18 millimetres. Therefore, J is 129.18 millimetres. And once again, we've resolved all of the unknown lengths on that triangle. The very slight discrepancy in those answers, where the first method gave us 129.19 and the second method gave us 129.18, was because this value that we calculated for the opposite was rounded to 2 decimal places. When we used that again in here, we incurred a slight error on our final answer.